Okay, I'm back. Now we're going to discuss page 5 of the section 2.3 notes. Here we are with example 10. And this is a great one. I love these problems. Ask anyone who's had me as a teacher before, they really know I like this because it really kind of forces you to think a little bit outside the box, use a little more critical thinking. The AP loves this too, or is this the College Board that writes AP. So expect to see something like this on the AP exam if it's back to business like normal with multiple choice, but we'll find out in the next few months how the AP is going to look. Anyway, you're asked to find the value of A so that this is continuous. Well, if you think about what this kind of looks like, just off to the side here, x squared plus 1, when x is less than or equal to 2, well, if I plug in 2 straight up, I do get 5. So that's going to be the far right endpoint. And if I just plug in values less than 2, like plug in 1, I get 2, plug in 0, I get this, and plug in -1, I get this. So it just kind of does this, right? Now here, this is negative x squared plus a. So, and it's starting at 2, obviously. So if I were to plug in 2 here, I'd have -4 plus a. Well, I have to guarantee, and there's a hole here, obviously, that this is continuous. Like I don't want this, you know, I don't want anything like this because then they're not linking up. So we need these to link up. You need both pieces to link up. So how are we going to do that? Well, formally, we are going to use the conditions of continuity. Use conditions of continuity. So first up, we need f of 2 to exist, which of course it does because you're told that when x is less than or equal to 2, use this expression here. So f of 2 equals 2 squared plus 1, which equals 5. Great. The second step, we need the limit. This is a big one, actually. Oh, that's a terrible looking star. Okay, a little better. Okay, third time's a charm. There we go. Very important step. Usually want to put stars next to something. You need the limit as x approaches 2 of f of x to exist. Well, that means we need LHL equal to RHL. We know this. We've done this many times. Well, I already know the RHL. The LHL, which is going to be, again, this right here. The limit as x approaches 2 from the left of f of x is going to equal 5. That's that. So for my RHL, I need the same thing. I need the limit as x approaches 2 from the right. And this is going to be the most important part right here. As x approaches 2 from the right of f of x must also equal 5. Well, if I'm coming from the right side, I'm using this expression. So -2 squared plus a must equal 5. Just like I had over here when I plug in 2. And I need to make sure, I need to figure out what the a value is so it matches up with y equals 5. That's all I'm doing. So essentially, you just plug in 2 into this instead of equal to this y value. That's really what you're doing. You want these y values, this is how they link up. You need both y values equal each other. That's kind of the quick and easy way. But I wanted to go over the formula with the steps of the conditions of continuity. But you need both y values to equal each other. So obviously when x equals 2 for the first expression, I got 5. Now x can't equal 2 because it's not included, but just include it. You get -4 plus a equals 5. So a equals 9. So you need this to be 9. It's a terrible looking 9. Oh, geez. This is why when your stylus is dead, it can be a little tough. So you need that to be 9. So if I were to graph that, that'd be pretty high up, of course. So see, 1, 2, 3, 4, 5, 6, 7, 8, 9. And of course, it's negative x squared plus 9. So you start here. If you plug in 1, you get 8. Plug in 2, you do get 5. If I plug in 3, then it's going to come back to the x-axis. So it's like that. However, we're only graphing a piece of it, the piece starting at x equals 2. Now, it's not included, so there's a hole there, but the hole's already plugged in from the previous expression, x equals 2. So you just really just do this. So that's your graph. And that way you force it to be continuous. You don't have to lift your pen or pencil off the paper. I don't have to lift my finger off the left button of my mouse. So a equals 9 is what forces this to be continuous. You'll have some horrible problems to help you with this. Now we're about to venture into the intermediate value theorem. And before we do that, let's answer this question. Why the big deal about continuity? Why do we care so much about this? Continuity is a very, very, so why do we spend so much time on this, right? It's a very, very important assumption for calculus theorems. And you'll see why when we go through all these different theorems, that if we don't have continuity, then things kind of collapse. So we need to kind of ensure that. And so we need to make sure we know what continuity is all about. So here's a new theorem. We had squeeze theorem earlier. So this one here is called the intermediate value theorem. For short, we call it IVT. And here's how it works. Let's say you got some function here, we'll call it f of x. And it's continuous, but it's continuous for a particular interval. Now, hopefully it's continuous for all real numbers, but that's okay. If you just find a particular interval from a to b, so a and b are x values, right? Remember, x equals a and x equals b. That's what this little thing right here means, right? This is why we spend so much time with interval notation for calculus. It just makes it easier to work with this stuff. Remember, we call it pre-calculus. We're getting ready for calculus. We're preparing for calculus. So let's say you choose an interval a and b, and f of a is right here, f of b is right here. So you're deliberately keeping your graph in between f of a and f of b, right? And in between x equals a and x equals b, it's continuous again. So it takes on every x value. That's the other thing too, is that, again, you have your interval x equals a, x equals b. Then you have the y values that go with x equals a and x equals b. And the graph f of x can assume, so f of x assumes any y value between f of a and f of b. And that's pretty much it. That is actually the intermediate value theorem. So this is actually your conclusion. Sorry I didn't make it sound like that. I actually made it sound like a conditional. So if f of x is continuous on this interval, that's what I should have said, then we know this is true. So as long as you're continuous on an interval, then fx, a graph, will assume any y value between f of a and f of b. So that's part of the intermediate value theorem. Here's another way of looking at it. if it's continuous on a closed interval, then any given y value, which we call d, in this, there'll be at least one occurrence where if c is in between a and b, then the y value of x equals c equals d, which obviously is in between these two y values. So if I had like x equals c here, wherever this y value is, f of c is in between f of a and f of b. Hence, why we call it the intermediate value theorem. Intermediate. Intermediate means be in between, right? Like, you know, your beginner level, your advanced level, your intermediate level, you're in between those two levels, right? So if you choose some x value c in between a and b, whatever that y value is, it's going to be in between the y values for my endpoints of my interval. So that's another way you can think about it too. So we will have an example on page 6.